Let's divide our full circuit into 7 sub-circuits to analyze one by one. First one is error generation part. In here, as you can see in this diagram, we use 2 LDRs which are mounted on the opposite sides of the solar tracker. And depending on the lighting condition of the environment, we got 2 individual signals from 2 LDRs, and those signals are buffered through the buffer circuits and sent to the differential amplifier circuits. In there, we got the difference of those 2 signals, and that's the error signal we got from the 2 LDRs. And after generating the error signal, we send that error signal to the PID generation circuit. In here, we use the PID controllers using operational amplifiers. After getting the individual P, I and D output, then we send those 3 individual signals to the weighted adder signals, as you can see in this script. Then we can get the addition of those 3 signals, and the output is the full PID signal.
Pulse width modulation, or PWM, plays a vital role in motor control circuits. Let's break down how the system works step by step. It all starts with a square wave signal generated by an A-stable multi-vibrator circuit. This type of oscillator creates a continuous square wave without external triggers. The frequency of the wave depends on resistors and capacitor values in the circuit, and variable resistors allows us to fine-tune it to match our PWM requirements. Next, the square wave is sent through an integrator circuit, typically built using operational amplifiers as shown here. This transforms the square wave into triangular waveform, keeping the same frequency. To ensure signal quality, the triangular wave is cleaned up using a precision rectifier, removing noise and ensuring accuracy. In parallel, the output of the PID controller is also rectified to prepare it for the comparison with a triangular wave. Now a comparator circuit as shown over here comes into play. It compares a rectified triangular waveform with the PID output. When the PID signal amplitude exceeds the triangular waveform, the comparator switches states, producing the PWM signal. The PWM signal is then conditioned by a couple of transistors as shown over here operating as switches. They ensure clean signals are sent to the motor drive IC. It's the L293DD motor drive IC used over here. The motor driver adjusts both speed and direction using logic inputs to control the motor's movement based on the switching action of these 2 transistors. This seamless interaction allows precise motor control, which is crucial for applications like solar trackers. With this design, the motor controller ensures efficient and precise adjustments, maximizing performance in systems like solar trackers. This video illustrates the generation of the PWM signal. As you can see, as we vary the lighting for the 2 LDRs shown here, the PWM signal's width changes. Alternatively, the duty cycle of the PWM changes. If we cover one end one of the LDRs, you'll see it saturating to one end, and if you cover the other LDR, it saturates the negative end, showing a complete change in the PWM signal. If you alternate both LDRs, the width or the duty cycle of the PWM signal changes accordingly.